or I'll forget. Okay, we are recording. So if you want to ask questions in the chat box, you can. If you just want to start talking, just make sure that you unmute yourself, because if you talk and I don't answer you, it's probably because I can't hear you. So you'll have to just let me know. And there are way more options on this thing than there were on Friday when I don't even know, like you could say yes, you could say no. Anyway, see if you have questions as we start, but I've tried to make some stuff available in, I'm trying to do this where it's not everybody's on here, because when I record it, you're on here. And now I can see everybody. Look at everybody that's here. Maybe you just woke up. Look at all these people. I'm glad you're here today. Or if you're on audio, you can just listen in. That's fine. All right. Well, you guys are just going to be up here. I can't make you go away. So we have, let me pick this out. Google Chrome. And there's a microwave in the background. Okay. So in As You Learn, which clearly you found because you're here, I tried to make a really defined block for where to go for lecture and then where to go for office hours. And did anybody try office hours? Because nobody showed up for it. Yeah, you have to make sure, Brianna, that your computer allows audio, and it's usually a setting right when you first come into the Zoom. I think I had some students in earlier classes, they left and then came back and then made sure to choose that option. But you can't hear what I'm saying because you can't hear anything. Maybe try to. That would probably help because she can't hear me. Anyway, in the computer on As You Learn, I had office hours, and I mean, it's new, so maybe you didn't, and that's perfectly fine, but they were there. It's in a totally separate link than the lecture. I'm hoping whenever I logged on before, did you see a waiting room? Did it have like a waiting room before I let you in? Okay, I've never used that before, so I was trying to see if that, and I had to like allow you to enter, which was really weird. So we have that. We have, I've put some stuff up in Sapling. It hasn't been a whole lot, but I think the end of chapter 3, there's a section, and then let's see if this will work now. The end of chapter 3 has a section, and then we're going to skip section 4.1. And then chapter 4 is huge. Chapter 4, I think we go all the way through 4.8. So just be really, really prepared for that, because it's going to be a really long chapter that we're going to do, I'd say, for a few weeks. But the reality is, I don't really know how long we're going to be doing this. I'm just trying to see if I can do, no, okay. We're supposed to spend a few weeks on chapter 4 anyway, and so we'll just have to see where we end up. We're going to skip section 1 because the material in it's not important, but we literally lost an entire week last week. Like I don't know. I don't know why they chose to do that with the college, but I don't think they're, okay, Jeremy, it's probably good that you mute your animals. I'd mute my kids if I could. But we'll do quizzes on here. Maybe by the end of the week, we'll try to have some kind of practice quiz where you take a picture of your work and upload it as a PDF. We'll try to do, I don't know how long we're going to be having to do this. It's not my choice. It's not your choice, but I'm glad we have this option so you don't lose out on your education for a whole semester because of this virus. But everything will be pretty much online until we can get whatever it is sorted out. So I will do the best that we can. I know you may not be comfortable with it, but I'll try to record it when I remember to. I'll upload it. I'll take attendance should you view and listen to it later or now. I've got it connected to my iPad, so I'll do notes. Any kind of handouts that we would have done, I can post in As You Learn. But otherwise, the effort on your part will have to up a little bit, because we can do this 4 days a week, but you're still going to have to do the homework, use the resources, ask questions, and I'll just do what I can. I mean, there's the stuff on Sapling is still, like the guided learnings are still there, and the questions are still there, and there's even some extra activities, and I can try to make some videos on content if it would help. But otherwise, we'll just come together for 4 days a week. If we can switch it to 3, have you do a work day, we'll see. But right now, we'll just try all 4 days and see what happens. And if you can make it, that's great. Because ultimately, you'll get a letter grade at the end of May, and you don't want that to fail because of all this mess that's going on. So we'll try. But I do have your tests graded. Your tests and your grades and As You Learn have been updated up through that last test through chapter 3. What I have not done is individually take pictures of your tests so that I can email them to you. So I will try to work on that. And if we need to, we can set out a day to look over them and see if you have questions. Because all chapter 4 is going to do is do applications of the derivatives. So it literally does all those derivatives again. So if you didn't get a good handle on them the first time, you have a whole nother chapter in which to do that. So you'll just have to see what it is that you were weak on, what it is that you need extra help on, and we'll just go from there. So I'll try to work on that. But like I said, there's 35 of you, and I don't know, was it 3 pages? They weren't terrible, but there were some low test grades and some high test grades, clearly. But those grades are in there if you want to see them. And then if you want to make a special office hour, that's up to you. I mean, I have capability. As long as I have internet and functioning technology, I can do this at 8 o'clock in the morning if I'm awake, and 10 o'clock at night if they're asleep and I'm still, I mean, all I have to do is launch this meeting and we can do this if you want to talk about anything. But you just have to give me a little bit of notice, and then we'll see what we can work from there. So we are going to do, there was one more section. Well, I guess I should say, do you guys have questions? Does anybody have questions? Because some of you were here Friday for this is how it's going to go, and then some of you did not. So does anybody unmute yourself and ask anything? Say anything? Anybody? You're good? Don't forget your video camera's on if you've turned it on. Again, you don't have to have it on, but I don't mind. I like seeing you. Some of you are in the dark. It's so dark out there. Okay, so there was one section left in chapter 3. And I don't want to spend a whole lot of time on it because of how minimal it is in moving forward. But I do want to at least let you do the homework for it. It was called, and it really wasn't even everything in section 3.5. It was like this one thing. Let's see if this will work. Maybe it will launch. Trying. Okay. It was called linear approximation. So I think in As You Learn, I uploaded the notes for it. And I think I've also uploaded a worksheet and maybe the answers to it. So what I would like for you to do is just read through linear approximation section and try some of the problems. I think there's even a few in the guided learning and see if you have any questions. But basically, it just revisits this notion of the tangent line. This tangent line, oh, that's not a red pointer. Let's try again. Here we go. So if you had a curve like the square root function here, and this is section 3.5, even though these aren't really labeled adequately. It took some kind of function, in this case, the square root function, and it found this basically like a tangent line. And it had you approximate values on this line using this linear approximation, which is just a linear function, this 1/8 x plus 2. But it's like this process that you had to go through with this formula that I've highlighted in this pink outline. And you basically just have to do like the function evaluated at the number it tells you to do, the derivative at the number it tells you to do, and then x minus the number that it, like this one is at 16. So it's a lot of function input and derivative usage to basically come up with a line, like a y equals mx plus b line. And it's this process that uses a line to approximate values that are really close to the number that you were looking at. So if you found a tangent line at 16, then you could use it to approximate the value of the function a little outside of 16, like at 16.1, 16.2, 16.3. Like if we look at here we go. Here's the square root function, right? And at 16, what was that? 1/8 x. I don't even remember what that said. Plus 2. Plus 2. So here's your tangent line at that point. And basically what linear approximation does is say you can get really close to that point and try to approximate values. I don't know if they'll let me do it or not. Try to approximate values at like 16. I won't even let me scroll, will it? No, it won't. But you can use it really, really close to 16 to approximate the function values, but you use the line. And I know you're like, I don't really see the point in this, but it's in this section and I was told to teach it to you. So you have different functions, but basically you have that same linear approximation formula. And if I give that to you on a quiz or a test, I'll give it to you. You don't have to memorize it. But you're just using it to come up with a line and then using the line and plugging in numbers, and then you'll compare actual to approximation. So just read through the examples. There's several of them posted. I'm pretty sure that I posted them in As You Learn. If not, I'll go back and do that after the class. But there's a whole bunch of these that I didn't even remember doing all these examples, but I guess I did a whole lot of examples. But it's a really short section and I'm not going to try to focus too much on it because there's no point in it. So, but that's the linear approximation. It's the end of chapter 3. That's the section that I cut out before I tested you because I didn't really feel like adding that to the test on top of everything else before spring break. So from there, we're going to move to chapter 4. Chapter 4 uses all of these applications of the derivative. And what it is, in a nutshell, is talking about first derivative is going to help us do, sorry, we got to check. So the first derivative is going to be something that's important to do something with, where it increases and decreases, where it has maximums, where it has minimums. The second derivative is going to be important for where it changes concavity, concave up, concave down. There's points of inflection where it changes. But there's like a whole section for each one of those. And then the end of it, we'll look at something called optimization, where we have, where you try to maximize volume for a 3-dimensional figure or minimize construction usage for fence building, or it's a lot of maximizing and minimizing. It's called optimization. And we'll do a few of those, but maybe not too heavy because, like I said, we lost a week last week, so we have to shorten something because I don't think they're extending exams. But to begin with, I have some notes that I had posted before, and I can put them up and then we can talk about them. So we're skipping section 1. Section 1 was a section called related rates, and it's not required for the course, so we're going to skip it. I'm not going to do it. And we're going to start with section 4.2, which is called minimum, maximum, minimum values, and then looking at critical numbers. So in chapter 2 and 3, we did derivative rules. We did lots of derivative rules, which I hope you haven't forgotten in the span of your 2-week spring break. But what we're going to do in chapter 4 are all those things I said that you needed to remember, because you have to know all of these derivative rules, because in order to get these critical numbers, you have to be able to find where the derivative is 0 or undefined. So this is where some of that solving, that simplifying, that factoring, that's where that's going to come in handy. So I tried to introduce you to it briefly, but now you're going to have to. you're going to have to be able to simplify it in order to solve these correctly. So section 2 focuses on this notion of critical numbers and also minimum and maximum values, which they're going to be what you think they would be. Like you have a graph, there's a maximum, you have a graph, there's a minimum. But when you look at it in terms of this notion of absolute, which is sometimes called global, I've seen some textbooks call it a global minimum, a global maximum. It's going to be different than a local. So I thought I would pop this up so you could see some definitions and then try to explain the difference, because even though min means min and max means max, it depends on whether it's absolute or local or relative or whatever you want to think about it as. So these critical values that we're going to find, a lot of times they'll use a C. They are specifically where the derivative is 0 or where the derivative doesn't exist. So being able to find where that derivative is 0 is important. And we sort of talked about it some in chapter 3, but maybe not too much. But as far as what absolute versus local means, so absolute, just to show you this, you're going to be told to look on some interval, like it'll indicate it. Like it may be on the domain of the function, or it may be from like 4 to 7 or 1 to 10, but it'll have you look within a little window and determine the absolute highest number, the highest function value, and the lowest function value for an absolute min or max. Local is sort of relative to your position, which is why we use this, not a highlighter. We use this relative term because you're going to be able to look at some, and that's why I have this highlighted and emphasized. You can move this open interval around to be like, oh, there's a high point, there's a low point. So I have this picture that I pulled from your textbook, fun graph, with all of these points, x1 through x8. And if you looked at this graph from x1 to x8, whatever those numbers are, here at x8 is the highest point on the graph, like of the function values. So there at this point, it has an absolute maximum. And the maximum value is whatever the function value is at x8. Minimums and maximums are always the y coordinate of the point, and they occur at the x coordinate, okay? But of that little weirdness that's there, which I might have to move over so you can see, that top dot is the absolute highest function value on this given graph. The lowest one, if you can see, and as far as function, it's on the y-axis. Here at x3, it is the absolute lowest minimum point on that entire graph. Okay, so as far as looking at whatever the graph is given to you, at x3, there's a minimum, and at x8, there's an absolute maximum. Okay, so absolute is on that given interval. Where's your high, where's your low? Okay, the difference between that and local is you can move around, imagine moving around some open, and that's the important part of this definition, interval, so that you have, I mean, just imagine, I'm hoping that you can still see my picture with this. You're trying to just imagine some little open interval that you're moving all the way around the curve, like if I draw on here, and it's open interval, so you cannot include endpoints at all for this local. But if I were to take like a, look between x1 and x3, at x2, there's a local maximum. It's not the biggest, highest point on the graph, but if I were to just like sort of horse blinder and look between x1 and x3, I have a peak at x2. So at x2, it's considered a local max. Same thing if I were to take that little open interval and move it, say, between x2 and x4. At x3, it's also a local along with an absolute minimum. So if I move that interval to include that low point, there's a local minimum there. Okay, it's continuous. It's no sharp point. I can take the derivative of it. None of those things are breaking any rules. So how about at x5? Do you think that would be maybe a local min, local max, anything like that? Anybody want to participate? Trying to click through all the people I can see. At x5. You have to unmute yourself though if you want to talk. Oh, we have some chat action. What's going on with the chat? Local max? Endpoints are considered none. Yeah, the endpoints are not considered local, but if you look for absolute on an interval, those they get included, but they don't get included for local. So yeah, x5 is a local max here. Because again, it's not differentiable there. It has a cusp, so it won't be differentiable, and it'll probably be somewhere where the derivative is not defined. But even though it's continuous, so if it's continuous, it can still have some sort of locality to it for a min or a max. So even though it's not differentiable there, it does have a local maximum at x5. At the sixth one, it's not really, I mean, I don't want to say nothing because it kind of flips from being concave up to concave down, which is going to be important in section, I don't remember, 4.5, 4.4, somewhere like there. 4.4. 4.4 is when that becomes important. But as far as it being a local min or max, if you were to affix a window around the x6 value, there's no min or max there. That is also not an eraser. x7 here, that's going to be a local min again, because again, the definition of local is you can take some indicated open interval that you choose, and between those two endpoints, not including them, like if I draw some parentheses around it, you have created an open interval in which there's a low point on the graph or numerically with the function value. Okay, but by definition for local, because it's an open interval, you can't include the endpoints because you'll just never quite reach that endpoint for it to be a local min or a local max. So they're absolute if you look on a closed interval. And depending on, like, we'll end up with some pictures, like here's a picture. Like if we do an exponential decay, but if I say to only look from like 0 to 2, that basically looks at you a window here. And at the top of it, that's going to be your absolute max. And here at the bottom is going to be your absolute min, but that it doesn't have any local minimums or maximums because you can't affix an open interval somewhere where it has a high point or it has a low point. Okay, so the definition for the absolute and the local gets a little confusing in this section. And I think to begin with, some of it, it just asks you to find critical numbers, which is just your ability to take and find the derivative and see where it equals 0. And then there are some questions that show up in this section that ask you to find what the absolute, and again, absolute is like 1. There's 1 min, there's 1 max. Depending on what the picture looks like I'm trying to think. Some of these piecewise ones get a little weird. Like if you were to do, you know, like you had a quartic function and it did that, it could have potentially 2 absolute max values, but it would still be the same value. Like if that occurred at 4, the absolute max would still be the y value of 4, even though there's 2 of them. Okay, so the minimums and the maximums are function values. So being able to identify it from a graph helps. And then the other part that you'll have to do is be able to take and identify it from the actual function in question. So if you had to do like, here's one. So the question would be, make this a little bit bigger, to locate the absolute extrema, which is just the plural for minimum or max. for x cubed minus 6x squared plus 9x plus 2. Okay, so that's a cubic function. It would technically have no high and no low because the ends go in opposite directions, you know, depending on, I don't know, we can graph it and look at it. But if I want to take that function and specifically look on the closed interval from 0 to 2, then on that closed interval from 0 to 2, it will have somewhere where the graph reaches a high point, and then we'll have somewhere where the graph reaches a low point. So to find these, to locate absolute extrema on some closed interval A to B, there's steps for it. So the first thing we'll do is we're going to find all the critical numbers, which are just where the derivative is 0 or undefined. So this one won't be too bad. And then the second thing that we're going to do is we're going to evaluate the critical numbers. Oh, we got somebody new. Here we go. Sorry, I'm trying to do like 3 different windows at one time. James, I'll look at the question. If you put it on a closed interval, they are considered absolute. But if you don't look on a closed interval, they're not. And the 4.3 problem, yeah, I'll look at the 4.2 question. It'll be good. So once you find where the derivative is 0 or undefined, then you're going to go through and evaluate the critical numbers and the endpoint values, like the 0 and the 2, and evaluate those using the original function. And then wherever the highest number is your max, and wherever your smallest number is your low. So we'll start, let's do the critical numbers first. So for critical numbers, let's find where the derivative is 0. I don't think we're going to have anything that's undefined because this is a polynomial. But if we do the derivative using power rule of a bunch of things added together, we get 3x squared minus 12x plus 9. It's not going to be undefined anywhere. So the undefined comes into play like with trig functions or square roots or rational functions where there's division by 0. So you always have to keep that in the background of where something's undefined. But this one is defined everywhere. Its domain is all real numbers. There's no restriction. So we're just going to see where this equals 0. So this is where factoring is important that you know how to do. And I tried to not really stress it, but to prepare you for it and say simplify it as much as possible. This is why you had to do that. So for this one, if we factor a 3 out, right, and we keep going, and what, x minus 3, x minus 1, 0 product property says if we have a bunch of things multiplied, we can set each of them equal to 0. The 3 is useless, but we get an x value of 3 and an x value of 1 as your critical numbers. Okay? So we are interested in any kind of absolute extrema from 0 to 2. So do you see how 3 is not in that interval? We are not using here. Like something happens there. But for this example, it's not in our given interval from 0 to 2. So we're not going to consider it for this answer for the question. Okay. So we've got 1 as a critical number. It's the only critical number that we're going to use. And we're going to use our endpoints. And we're going to take them and plug them back into the original function and see where we get our high and our low. Okay, so that's this next step, is we're going to use x equals 1 and the endpoints of 0 and 2, and we're going to plug them into the original function, the cube one, the x cubed minus 6x squared plus 9x plus 2. So we're just going to plug them back in. So if I do f of 1, I mean, again, just plug like 1 cubed minus 6 times 1 squared plus 9 times 1. I mean, you just plug it in 1. Last time I got 6. That's 6 again? Well, yeah, you get 6. If you evaluate the function at 0, again, this is not, it's not into the derivative, it's in back into the actual function. You get 2, and if you plug 2 into the function, I'm talking 2 cubed minus 6 times 2 squared, following order of operations, evaluate the function at 2, you should get the number 4. And of those output values, which one is the smallest? The 2. So since that's the smallest output value, that is where you have your absolute min at that endpoint of 0. Since 6 is the largest, right out of space. 6 is the largest function value that we got for an output. So that is where we have an absolute maximum on that given interval. Again, it's not for the entire function, but there are a few questions that just say, hey, look here, where's the high, where's the low? And I know you have graphs and calculators and you can graph them and use them, but this is using calculus. And this is what you're expected to do for this course. And we can look at it too. We can look at the function. Because like I said, it's not, we're not always going to look on intervals, but it's just having you look at things a little more local instead of the whole picture. 9x plus 2. So here's the graph. I hope you can see that really well. So it has, again, I wish I could write on the screen, but I can't. Where it has that max, if you did an open interval, it has a local max, it has a local min. But if you open it up to the whole domain, it doesn't really have absolute ones. But if we restrict it and just look from 0 to 2 on the x-axis, you can see that on the left-hand side at 0, that it has a minimum. Again, we're looking absolute on this fixed interval from 0 to 2. It has a local, an absolute minimum in that a fixed window, and then at that peak, that, where was it, at 1, it has that maximum value of 6. So again, we're not looking at the whole picture, we're simply looking from a fixed interval 0 to 2, where's the low, where's the high. Sometimes it's in an endpoint, and sometimes it's somewhere in the middle. Sometimes it doesn't, well, it'll always have one if you look on a fixed interval. But this is just, again, the directive is finding local extrema, or locating absolute extrema on some fixed interval. That'll be the process that you'll use for these whenever you go through them. And depending on the function, these could get a whole lot harder. I have several examples. I don't know which you would like to actually talk about. Let me get another piece of paper here. Like if we did this x to the 1/3, which is the cube root of x, and we looked from -1 to 1, and we wanted to find any absolute extrema. In your textbook, it talks about if you look on a continuous function on a fixed interval, it will have a high and it will have a low. It's just by definition, it's going to have both on one end or the other or somewhere in between. So if we want to find the absolute extrema here from -1 to 1, you could look at the picture if you want to, but the expectation is that you find the derivative and see where the derivative equals 0. So let's find any critical numbers, which is where the derivative equals 0 or where the derivative is undefined. And this is why you do 2 chapters worth of derivative rules, so you can do these. So if we do power rule, we bring down the 1/3, keep the x, subtract 1, which is the same as 1/3 x to a positive 2/3. So nothing will make this 0. It's a rational function now. Nothing will make this equal 0. And remember, the focus here is the numerator, because nothing will make the top zero, but do you see where the function is now undefined? And we've created this rational function. It has x in the denominator. X being 0 is now a problem. So this derivative is undefined at 0. 0 becomes a critical number. Even though it doesn't make the derivative 0, it makes the derivative undefined. So the critical numbers here are just going to be 0. Okay? So to find the extrema that it will have, we evaluate the original function at the 0 and also the -1 and 1 endpoints. Because again, we're looking at a fixed area, including those endpoints, and so we want to see where's our high and where's our low. So if we do f of 0, f of 1, f of -1, and we'll see what happens. So our original function was x to the 1/3, which is the same as cube root. So if you cube root 0, you get 0. If you cube root 1, you get 1. If you cube root -1, you get -1. Or you can raise them to the 1/3 power if you want to. And of these, 1 is your largest. It's the largest answer. It's the largest output. So it has an absolute max of 1 at the x value of 1. And the smallest is -1, smallest for output value. So it has an absolute min of -1 at x equals -1. Again, the absolute, the extrema here, the minimums and the maximum, is the y value. Even though this is a poor example to show you the difference between the two. That happens a lot. But the extrema itself, sometimes you'll be asked where it occurs, sometimes you'll be asked what it is, sometimes you'll be asked the coordinate point for which it happens. You'll just have to watch how the question wants you to do the answer. The cube root, the 1/3 function, x to the 1/3, looks like this. It's like the cubit function got laid sideways. So we only looked from, where did it go? -1 to 1. And in that window, if you can see the graph correctly with zoom here, you can see that down there at, I don't even think I can like point. Nope, sure can't point. Oh, can I use my mouse and point maybe? You can see my mouse. Here at -1, we have the lowest part of the graph, and here at +1, we have the highest part of the graph as far as a function value. So again, I know that some of you are going to pull this from a calculator, but you're going to be asked to use calculus to show how to do it. And that's the process. Anytime you're asked to find extrema on a fixed endpoint, you find the critical numbers, and then you plug those and the endpoints back into the function, and then high is the max and low is the min. It'll always have one if it's on a fixed interval. Does anybody have questions? I can open this up, see if you have. Some of you like to chat and some of you like to talk. And some of you won't ever say a single thing. So, anybody?
So what exactly is the difference between a absolute and a local? Because is it just the way you define the interval?
It is. So the absolute is going to be on some, what would be the right way to explain that? If you do absolute on a fixed interval, on that fixed interval, it's the highest high and the lowest low. If you look on like a domain of a function, it may not have one. So absolute is like the absolute highest in that picture that you're told to look, and the absolute lowest where you're told to look. Local, I like to think about local as having like little horse blinders and going around the function and trying to figure out, okay, if I go here, where's my minimum? If I go here, where's my maximum? So local has, and that's why I say, wherever that slide went, where the local is going to be on, you can take that open interval and move it anywhere you want to. Absolute, you cannot. Does that make sense?
Yes. So the ones we've done have been the absolutes because we've had a like clearly defined interval.
Yes, and I think that's actually part of the directions. It'll say find the absolute minimum and absolute maximum on this fixed interval.
Okay.
And I'm trying to, and to begin with, I think in section 2, that is all you're really focused on finding. Visually, I think would be the only, let's see, is it in your textbook? It was in your textbook. Please don't turn the textbook off. Work with me today, computer, iPad, maybe sitting here spinning. That's fantastic. The picture ones are the ones where a lot of the times you'll see the local. Is this it? I'm trying to share this with you so you can see it again. Here's one. Maybe my phone would stop dinging. Here we go. This picture, like we did this picture in identifying local and whatnot, but here would be another one. So distinguish between local versus absolute. You know, X2 and 3 would be local maxes. So would X6. And then local mins would happen at 4 and 7. But 7 is your absolute min, 8 is your absolute max. But if the local, you can just move around and find them. And when we move into, I think it's section 3, where we look at where it increases and decreases, we'll be looking locally. Because when we find those critical points, that's going to tell us where we have those minimums and maximums in the graph. Does that help?
Yes.
Anybody else? No more chats. Going once, going twice. A lot of the things that are in section 1, as far as the homework goes, I think deal with absolute. There's some piecewise questions, which we can look at some more of those tomorrow. But a lot of it has to deal with your ability to take a function, and I'm trying to see one that I did before. Yeah, that one was fun. What kind of time do we have left? 6 minutes. Here is one. Let me share my iPad back with you. Oh, not that. Maybe not the book. So if you had to do one, I was trying to think of one. Here was one. Critical values. Critical values are something that you're asked to find because you're going to use them like the rest of this chapter. So if you had to find, and they're also helpful to find extrema. So if we had to find the critical values for this function, do you know what you'd have to use? Critical values are x's wherever, that's not how you spell wherever, the derivative equals 0 or where the derivative is undefined. And I want to put this note here that the critical numbers have to be in the domain of the function. We haven't really run into that yet, but we will. Domain of. All right, but my first question is, how do you get those critical numbers? And this is where chapter 2, 3 come back in. Because in order to get the derivative, guess what we have to use? Anybody want to share? Quotient rule. Yep, that's exactly what we have to use for this. And it uses power and it uses chain, and all those things that you thought might have went away after you took that test are back into this chapter. So that's why I said it's really important that you got a grasp on those, because we're going to literally use them all in chapter 4. So the derivative on this guy, I'd almost let you just try it and then we could come back to it. But I think we might have 4 minutes, so I'm going to use them. So the derivative of the top, 2/3 x minus 2 to the negative 1/3. If I chain the inside, it's just 1. times the derivative of the bottom minus derivative of the bottom times the top all over the bottom squared. So this is where it's super important that you know how to simplify it, because otherwise you're not going to be able to tell me where this, you can tell me where it's undefined, like at 0, but that's about all you could tell me right now. So if we play some cleanup, which is what you're going to need to be able to do, trying to see how you want to, there's going to be some fractions and fractions. So like this first part here, the x minus 2 to the negative 1/3. So there's a 2 and an x in the top and a 3, and then this x minus 2 comes downstairs. And then there's an x minus 2 to the 2/3, and that's all over x squared. So the goal here would be to try to rewrite the entire thing as one single fraction. So maybe you didn't think it was important enough before, but now you have to if you want to get it in the right format. So if you can get a common denominator across the top, combine like terms, flip and multiply, which I'm trying to see how my time is. We're doing good. So common denominator, share the denominator. 3 with x minus 2 to the 1/3, 3 x minus 2 to the 1/3. So we get a 2x minus these two, because you're multiplying with the same base. If we add the exponents, it's just x minus 2 with a 3. Like, that's just the way it works out. They combine something to the 2/3 times something to the 1/3. If you add exponents, it just becomes to the first. There's 2/3 plus 1/3 is 1. So we have that over 3 times x minus 2 to the 1/3 all over x squared. If we distribute, clean up, combine like terms, 2x minus 3x, what would that be? Plus 6 over 3 times x minus 2 to the 1/3. And this half, this x squared that we divided, I'm going to flip it and multiply it. So it's 1 over x squared. So instead of single x squared, we'll flip and multiply it. Make sure nobody's trying to do this. Okay. So then we get 6 minus x in the top and 3x squared times x minus 2 to the 1/3 in the bottom. Now you can tell me where that is 0. The numerator gives you a critical number of 6, and the denominator gives you undefined critical numbers at what, 0 and 2? It's what makes the bottom 0. So the only thing that we have to watch out for is anything that's not originally defined or originally in the domain. So we got a 6, and we got a 0, and we got a 2. But 0 is not in the domain of the original function, so it's not considered a critical number. So the only critical numbers we would report here are 6 and 2. And if all you have to do is say what the critical numbers are, then you can stop. If you have to look on a certain interval, then that's when you start plugging in stuff. But 6 and 2 are important numbers for this function, and we will use those in section 3, 4, 5, and 6. I think we use them in all those. But this is revisiting your ability to take the derivative and clean it up. And that's why I cannot stress, I tried in chapter 3, but it is extremely important that you have the strong algebra to be able to combine those. And if that's what you need to work on, that's what we'll work on. Or that's what you can work on. You can come to office hours. The math lab is actually still going to run virtually like this. We'll move this back on here. It's still going to operate 4 to 7 p.m. Sunday through Thursday, but it's in this atmosphere. It's, they've got them on Zoom, they've got them with things to write on, and it's a totally separate Zoom session that I can send to you, and you can get logged on. But I'm happy to do this with you. I have office hours if that works for you, and if they don't, if you try to give me an hour or so in advance, I can set something up and meet with you, and we can talk about calculus. But otherwise, it's a lot of derivatives. This whole chapter is derivatives, and I'll try to get your test scanned and back to you. We can talk to them because it's kind of important that you understand how to do those so you can do them in chapter 4. But does anybody have questions? Pull up everybody that's decided to share. We got the head shaking. You're like, it's hard to get back into math mode after 2 weeks of spring break. I'm with you. I get it. Okay, but I've recorded this, and it takes like 10 minutes to upload to my computer and save it because it's, 50 minutes long. But then under the weekly block, I'll just post lecture for Monday, March 23rd. And if you need to go back and look at it, you can. And if, you can't join us on Wednesdays because that's when your boss scheduled you to work at 1 o'clock, log in and look at it later. I can see that you're here. I can see that you look at it later. Start the stuff in Sapling when you can, and I'll put up some more items. The due dates are really fluid, so start them. They do have due dates on them right now. They may change. I don't really know, but we do have to get through the material with a little bit of haste. My office hours are normal. Yes, 9 to 10 and 12 to 1, but 0 people did them today, which is okay. But I plan to have them on. I think it's supposed to notify me if someone logs in, but you have to click on, just make sure that you click on, share my screen one more time. Within your calculus course, make sure you click on that says click this link for virtual off. Make sure you click on that Zoom link because that's a completely separate meeting ID than the lecture that we're in right now. And I use that office hours for both classes. So that's why it's a different link. So as long as you're in there, and if it's not working, you can email me to say, hey, I need to do some office hours. Can we meet? You just, like I said, give me an hour or so because the email, sometimes they come through on my phone immediately. Sometimes they take 4 hours. I don't really know why. And I am at home with my kids. So there's that. But if you don't have questions, James, I'll look at that question that you had and we can see, because you're right, they are worded. It's the weirdest section in the way that things get worded, but we'll make it work. We'll do what we can, but you gotta up your part and participate and ask questions and look at you guys with your cats and your dogs. I see a little dog eating cat. I'm surprised my children aren't running around with wolf ears like they have all week. Okay. All right. We'll see you tomorrow. Let me know if you have questions. Bye.